hole in a uniform polycarbonate plate. So, to start off with, we have the setup of the program. In the basement of the LSRM building, we set up this setup, which this right here is the uniform polycarbonate plate. These sensors right here are the stress strain sensors, and we have them oriented vertically and horizontally. This is the hole in the middle of the plate where we're going to be doing most of our analyzing. And this light behind is just a light so that on the video you can see the different polarized lights that are crossing over the plate. This is another image of the setup, just showing where the video camera was oriented so that you can kind of see which angles the videos later on in the presentation come from. So before we did our analysis, we did some predicting for our project. So these are the predicted values of the stress along the hole in the plate. And the graphs you see are concentrated on the y direction over the cross-sectional area of the plate. So as you can see, as you get further and further away from the center of the hole, which would in effect be right there, you have less and less stress, and then it increases as you get closer and closer to the hole. So this is the bottom half of the plate, and this is the top half of the plate. And these two graphs composite show the overall stress distributions over the center line of the plate. So next we modeled the plate in SolidWorks to kind of get a feel of what the different the deformations and the stress concentrations are going to look like. So this is a plate, it's a model of 1/4 of the actual polycarbonate plate tested in the lab. And here is 1/4 of the 1-inch radius hole. And we made a mesh go all over this plate so that you could see the different stress concentrations. The mesh is a lot more fine around the hole because we're expecting there to be more stress concentrations around that section. And then as you move further out, the mesh gets a little more coarse because we don't expect as much stress in those areas. So after we ran the SolidWorks simulation, this is what the graph we got. As you can see around the hole, as expected, there's a lot higher values of stress. And then the rest of the plate, as you move further out from the hole, gets pretty much uniform. The plate was restricted with symmetric boundaries on these two ends and a rolling boundary on the back side. And then the large purple arrows in the corner show the force and tension that's stretching the polycarbonate plate. And as you can see, there was some severe deformation that the plate underwent under this simulation. So this is a zoom in of the normal stresses on the plate. So it just gets you a little closer to the whole area where you see the variety of stresses and the higher values, and then shows how quickly they drop off as you go throughout the rest of the plate. Now we look at the shear stress in the plane of the plate. So as expected, again, the higher shear stresses are around the hole, but it has kind of a different distribution with lower overall stress levels. But this shear stress is acting along the XZ plane. And so it's just a different kind of stress, and it's compared with the normal stress in the slide previous.
You guys can load it up, unload it, stop it wherever you want, but we're not going to go over 2,000 pounds. That'll make sure that we try to stay out of the
Now, material, polycarbonate.
That's so cool. Oh, wow, look at the Windows 2000.
What about lights?
The laptop's pretty sweet.
Lights off?
Yeah, lights off would be good. Yeah. Just the screen. That's
that good?
graph of the comparison between the
theoretical predicted values of the stress along the normal stress in the plate along in the y direction with our experimental stress in the y direction. The red dots correspond to the experimental values that correspond with the 5 strain gauges in the vertical direction with increasing distance from the center of the hole. The blue line corresponds to the theoretical stress that would have occurred along the HH line of the plate, which goes through the center of the hole, where the maximum stress would occur. As you can see, the experimental data lines up relatively well with the theoretical data, however there are some errors. And here's Jay to explain the errors.
As Tiger Woods has shown us, everyone makes mistakes. And in our comparison between the theoretical and actual values, it's not completely perfect. There could be a couple of reasons for this. The one major reason is that there are a range of values for polycarbonates, Young's modulus, and Poisson's ratio, and we had to choose one value to use, but perhaps if we'd changed that within the range, then the graph would fit a lot better. A couple of other reasons are that SolidWorks did our finite element analysis in an ideal situation, in an ideal environment. And, of course, our actual experiment was in a real-life environment, which would make a major difference.